All right, lesson 6 is just proofs. So it's nothing new, but it's just going back over how to prove all these wonderful rules that we've been learning. Okay, and this will make it so that all of your proofs is on the same page. Okay, so let's go back over the proof for product rule. Essentially, why does it work? Now we remember that the product rule says that if we have something like this, if we have two numbers with exponents being multiplied, we're going to add the exponents. So this would look like 5 to the 3 plus, to the 3 plus 4, which equals 7. Okay, so what's the proof though? Why does that work? Okay, so we should remember that 5 to the third means there's 3 5s. And 5 to the fourth means there's 4 5s. So the reason the product rule works is because if we expand these out and count up how many there is 7 5s. Okay. Next one is the quotient rule. Oh wait, let's go back. Sorry. I want to show you an example of the product rule and a proof of the product rule with a negative exponent since we know those now. So let's say I had x squared times x to a negative third, okay? Because you can still expand this out, okay? So if we just do the product rule, we would do 2 plus a negative 3, which equals a negative 1. And so we know we can't leave it like that, and so this equals 1 over x to the first, or just 1 over x. Okay? And so how would we prove that? How would we expand that out? Well, x squared just means there's 2 x's, and x to a negative 3 means there is 3 x's, but they're not on the top, like this shows. It's actually on the bottom. Okay? So if we expand this guy out, it's actually 1 over x times x times x. Okay, so if we combine these, you have 2 x's on the top and 3 x's on the bottom. And now we're actually getting kind of closer to the quotient rule where we know that we can cancel out top and bottom, and what's left? Well, there's 1 on the bottom. Okay, it's a little messy. Okay. So now let's actually go to the quotient rule. Okay. Our quotient rule says that when we have numbers with exponents that's being divided, and they have the same base, we can subtract the exponents. So this would become 4 minus 2, which we know to be 2. Okay, so this is just 7 squared. But why does that work? So once again, let's expand it out. The 7 to the fourth means we have 4 7s, and the 7 squared means we have 2 7s on the bottom. Then you just look what we can cancel out. A 7 over 7 just equals 1. A 7 over 7 equals 1. So you're essentially saying you have 1 times 1 times 7 times 7. And we know that multiplying things by 1 doesn't change the answer. So we can really just pay attention to these two that are left. And so there's 2 7s left over. Okay. Let's look at an example now with negative exponents because we love those now. And we're experts on them now. Okay. Now the regular quotient rule says because we have the same base, we can take the top number and subtract the bottom number. A negative 2 minus a 2 is negative 4. We know we can't leave it like that. So 1 over y to a positive 4 is our answer. So what would this look like if we expand it out? You have to remember that this negative exponent means you don't actually have 2 y's up here. You actually have two y's on the bottom. Okay, so let's show that. So this top part means we have 2 y's on the bottom, And then this bottom y squared means we have 2 more y's on the bottom. And so we're actually left with nothing on top, but we can't say that there's nothing. There's actually always a 1 there. Okay? Well, add it up. What do we have? We have 4 y's on the bottom. You can see that it's almost faster than just doing the quotient rule. Okay? All right, let's look at the power rule next. All right, so remember the power rule says that if we have an exponent raised to an exponent, we can multiply these together. Okay, so this would become 3 to the second times 3. So this is just 3 to the 6th power. Okay, so let's look at how this works now, what this actually means. So this means that we have 3 squared 3 times. 3 squared once, 3 squared twice, 3 squared again. Okay, so this is another way we could prove it. We could then do just the product rule, add all those up, and it will still equal 3 to a 6. But let's break it down a little bit more. So let's break down each of what these are. So now we're essentially going back to the proof of the product rule. Well, this one means there's 2 3s. This one means there's 2 3s. And this one means there's 2 3s. So count them up. We got 6 3s. Okay. So here's a short way to prove the power rule, but then you essentially kind of have to prove the product rule right afterwards. Okay. Let's look at an example with negatives. Okay. So our regular power rule said that we would multiply these. So we'd have an x to a 3 times a negative 2, which we know to be negative 6. We can't leave it like that, so we put it under 1 and change the sign. Okay, so why does this work? So this negative 2 means that we don't have 2 of this, we actually have 2 of it underneath 1. Okay, so this means we have x cubed once, twice. Okay, and again, we could just do the product rule from here, add up the exponents, they stay on the bottom. Or we could expand this out once again, essentially proving the product rule. So this means we have 1 over x 3 times. This means we have 1 over x 3 times. And you could be thinking about it like this, or you can be thinking about it 1 over x, 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 and 1 over x, x, x. It's actually the same thing. So either way you like looking at it, if you want each x to have their own 1, or you want them to share, it doesn't actually matter because you count them up, there's still 6 x's on the bottom. Okay, and that's how you prove the power rule with negative exponents. All right, distributive property. So let's say we had x and y to a 3rd power. Okay, our distributive property says you just take that and throw it on each one. And luckily, since there's nothing inside, you don't have to worry about multiplying anything because there's always a 1 and you're essentially doing 3 times 1, but we know that's still 3. So it'd be x 3rd and y to the 3rd. Okay, so why does this work? Well, once again, we'll just expand it out, see what it looks like. So this 3 says that we have everything inside 3 times. So there's, oops. So there's 1, there's 2, and there's 3. Then, adding like terms, we have 1, 2, 3 x's, and 1, 2, 3 y's. Okay, so there's a proof of the distributive property, and hopefully you're noticing every way to prove something is just expanding it out. Okay, going back to basics. All right. Let's take a look at a negative. So let's say I had, I don't know, let's change it up, xz to a negative 2. Okay, distributive property says we put each of those, the negative 2 on each of those, so x negative 2, z negative 2. We can't leave those there, we have to move them so that they become positive. Since they're both negative on the top, we move both to the bottom, 1 over x squared and z squared. Okay, now let's prove it, so meaning expand it out. This negative 2 means we do have each of these twice, but they're not on the top like they look like, they're actually on the bottom. So this means we actually have 1 over xz and another xz. Okay, so now we just kind of combine things that we can. There's 2 x's on the bottom and 2 z's on the bottom. Okay, same thing. And it wasn't actually that much longer to do that way. All right, let's take a look at 0 power. This is the last one, I promise. Okay, we've seen a couple ways to prove 0 power, so I'm just going to go through them really, really fast. Let's do 2's. Okay, and I've thrown in a negative 1 just so we can see what happens. Okay, so 2 to the 4th is 16, if I'm not wrong. This is 8. This is 4, 2. So we can see each time it's dividing by 2, so 2 divided by 2, so this has to equal 1. So 2 to a 0 has to equal 1. Okay, that's one of the proofs for proving that anything to a 0 equals 1, because you can do this with each and every number. Okay, let's take it one step further and let's explore the negatives. If I, once again, divide this by 2, you get 1/2. And that should make sense because the 2 was on the top with negative, and it goes to the bottom and becomes positive. Okay, so that's actually another way you can prove negative exponents if you really want to. Okay, the other way to prove 0 power was to just show that you can multiply or divide anything by something to a 0 power and it doesn't change the identity of it, just like 1. So let's say we had 3 squared times 3 to a 0. Our product rule says we add those. Well, 2 plus 0 still is just 3 squared. So because nothing changed, this guy has to equal 1 because it keeps the identity of 3 squared. Let's look at it with the quotient rule. Let's say we had 7 to a 3rd over 7 to the 0. Our quotient rule says that we subtract. And once again, our 7 to a 3rd hasn't changed identity because 7 to a 0 has to equal 1. Okay, so there's many, many ways, and you could even do it with other numbers. You could do it with variables if you wanted to. They all prove 0 power. Okay, and that's lesson 6.